I thought it'd be interesting to train a random forest classification model and see how it performs compared to a coin flip in making predictions. I'll be using the Python programming language. I'll build a random forest classified model to predict fitness class attendance. For example, when a customer books a fitness class, do they actually show up to the class? I'll show you which performs better over 5 predictions, either the random forest model or the coin flip. I'll also show you the Python code to train and test the model, as well as produce metrics for evaluating the model. Because in reality, you'd use a much larger test data set to evaluate the model, and also more rigorous metrics such as precision and recall, an F1 score. A random forest classification model is an ensemble method which is built up on multiple decision trees. Each tree is trained on a subset of the training data. The random forest uses voting to determine the predicted class. For example, each decision tree from its inputs will predict a class, and the class which is predicted by the most decision trees will be the random forest prediction. For the fitness class random forest classification model, the output will be whether the customer attends or does not attend, and it will take as inputs the day of the week of the class, the number of months the member has been a member of the club, the weight of the member, the number of days before the class the member booked the class, and time, which is whether the class is in the morning AM or in the afternoon PM. I downloaded the dataset from Kaggle. It's a fitness club dataset for machine learning classification. The fitness club is based in Canada. I split the dataset into a training and test dataset, and then I randomly selected 5 data points from the test dataset for the coin predictions. I used flipsimu.com to generate the coin flips. A coin flip of tails will be assumed to mean not attend, and a coin flip of heads means attend. For the first prediction, the random forest model took the inputs and predicted not attend. Then the coin flip was tails, so the coin predicted not attend as well. The actual result was not attend, so the coin and the model both had a score of 1. I'll now start talking you through the Python code. I needed to pip install NumPy, pandas, matplotlib, scikit-learn, and imbalance-learn. I then imported train test split, random oversampler, random forest classifier, accuracy score, confusion matrix, and classification report. I began by loading the dataset using pandas read CSV, and then just printed the data to have a look at it. For the second prediction, the coin flip again was tails, meaning not attend, and the random forest model also, given the inputs, predicted not attend, and the actual result was not attend. So now the coin and the random forest model were 2 each. In the Python code, I then checked the data type. I'll use this information later to convert various variables to the appropriate types, because sometimes types are loaded as object when we really want them numeric in the model. I also checked whether there was any null values in the dataset using is null. Here you can see that the weight variable on the right hand side, booking ID, months as member, these are all variables in the dataset. And you can see that the weight variable had 20 instances where the weight was null. What we're predicting is the variable attended. So I wanted to check whether the data set was balanced or imbalanced. When I say balanced, as in, is there an equal number of attended and not attended data points? I used the following group by and count to do this. Here you can see that it was 1046 not attend data points and only 454 attended data points. So this is an imbalanced data set. Depending on the type of the classification model you're training, an imbalanced data set can lead to a bias model, which is more sensitive to the majority class. So later I will cover how you can convert an imbalanced data set to a balanced data set, which may improve the model's ability to predict the minority class. Some of the data variables were loaded as objects, so here I'm just converting them to numeric, using pandas to numeric. I'm converting days before, which is the number of days before the class the booking was made, and converting that to a numeric, as well as a class we're predicting attended, which will have values 1 or 0. 0 means not attend, 1 means attend. This is just cleaning the data. I then dropped rows from the dataset which had null values using drop-NA. I then extracted the attended variable we're predicting into a Y variable. For the third prediction, the coin flip was heads, which means attend, and the random forest model predicted not attend. Here the actual result was attend, so the coin is now leading 3-2 over the random forest model. The dataset had a category and booking ID variables, which I won't be using in the model, so here I'm just dropping them from the data. Again, as part of cleaning the data, the day of the week, I wanted to check whether this column has unique values for each day. I'm using value counts to check this. So here you can see Friday has 271 data points and 26 have a value FRI dot. So we want to clean this data up so each day of the week is represented in a unique way. The following code, cleaning the day of the week variable, replacing FRI dot with FRI. I did a similar thing, replacing Wednesday with WED, as well as Monday with MON. I then wanted to check the time value, which is the time of the class, whether it's uniquely represented, and it was. It was only using AM and PM in this variable. Here I'm getting a list of the categorical variables in the dataset. These are day of the week and time. Categorical variable is a variable which has different classes. So for example, time has classes AM and PM, so it's not like a number. And same with day of the week. We'll have a class for each day, such as MON, WED, SAT, etc. Now we can deal with these by converting them to one-hot encodings. I'm checking the data types for type object, determine these categorical variables, and then I'm printing them out. To convert a categorical variable to one hot encoding, for each possible class value of that variable, you create a new variable which can have either the value 1 or 0. So for example, day of the week, there'll be a new variable, day of the week Monday, day of the week Tuesday, day of the week Wednesday, etc. for each particular day. And each of these can have either the value 1 or 0. So if you've got a data point which is on Monday, day of the week Monday will have the value 1, and all the other variables, say day of the week Tuesday, day of the week Wednesday, will have the value 0. So that's how you capture the day within the data. I'm using pandas get dummies to convert these categorical variables into new variables which are one hot encoding. This will only affect categorical variables in the feature to encode list and leave all the other variables untouched. I'm now splitting the data into a training and test data set using train test split. This will result in a third of the data as a test data set and 2/3 as a training data set. For the fourth prediction, the coin was heads, meaning a 10, and the random forest model from the inputs predicted not a 10, and the actual result was not a 10. Now the scores are coin 3 and random forest model 3. Because the data was imbalanced, I used oversampling to create a balanced data set. I'm using random oversampler and calling the method fit resample on the training data. Oversampling works by taking a minority class and randomly sampling elements from it until you have equal numbers of the minority class and the majority class. And when I'm printing out the count here, you can see there are 677 points now of not attend and 677 points of attended. Here I'm now creating the random forest classifier. N estimators means the model will generate 250 decision trees, and I then call fit on the training data to train the model. Then using the test data set, I call predict to produce the random forest model's prediction. I then use the accuracy score, passing in the model's predictions and the actual test values, and then print out the accuracy. So 76.3% of the random forest model's predictions were correct. Because we started with an imbalanced data set, the test data set will also be imbalanced. And so we need to use other metrics such as precision, recall, and F1 score, give a more rigorous analysis of the model's performance. For example, with an imbalanced test data set, you could have a naive model that just predicts continuously the majority class, and in this case, continuously predicts not a 10. And if the data set is highly imbalanced, that may produce a high accuracy, but this is just a naive model, where in reality it's not sensitive to the minority class. So here you see the results on the right hand side. In the first column you see 0 and 1. 0 means not attended class in the test data set, and 1 means attended. And you can see there are 339 not attended data points in the test data set and 146 attended. There's 485 data points in the test data set altogether. For the not attend, there's a precision of 0.84, which means when the model predicted not attend, 84% of the time its predictions were correct. Recall is a measure of how sensitive the model is to the class. So for example, for not attend, it has 0.81, which means the model was able to predict 81% of the not attend values in the test data set. F1 score is a harmonic mean of the precision and the recall, so it takes into account both precision and recall. For the attend, it has 0.6 precision, which means 60% of the model's predictions for attend were correct. And recall of 0.65 means the model was able to predict 65% of the attended values in the test data. So the model was more sensitive and better able to predict not attend events than attend events. And the accuracy of 0.76 was what we've previously seen, just a basic 76% accuracy. Ideally, your model will have high precision and high recall, but often with models, as the precision improves, the recall drops, and vice versa. With low precision, there's greater recall. And it depends on the business case, whether you require high precision or high recall. So for example, if you're using a model to determine when to buy a stock, you would want high precision because the downside of making the error would be great. So if you're interested in fraud detection, you'd want high recall because the cost of missing a fraud event would be great. And if the model indicates a fraud event but it isn't one, you can always investigate. False positives are when the model predicts an event but it's incorrect. And false negatives, an event occurs but the model has failed to predict it. To determine which features were most important in the model, I've created a plot using the classifier's feature importances attribute, and I print the top 15 important features. You can see that the number of months as a member has the most influence on the model in determining its predictions, then followed by weight of the member, and then the number of days before the class when the booking was made. For prediction 5, the coin was heads, meaning a 10, and the random forest model, again, given the inputs, predicted not a 10, and the actual result was not a 10. So the random forest model beat the coin 4-3. In reality, you would not consider these 5 predictions significant. You'd really be looking at the larger test data set, precision, recall, and F1 score, and considering it in relation to your business case. What's more important, precision or recall, or whether you need a balance of the two.